Sure. Yeah, I hope this is better. Yeah, so I'm going to start with the very basics here about planetary systems. And this is not something obvious for many people, that planetary systems are actually really complex. Not, we tend to imagine just a star or a couple of stars if you're fans of Star Wars, and some planets revolving around them. And that's a very, very simplistic view of what's going on, because we actually also have a lot of minor bodies. It has been recently announced that Saturn has way over 100 moons, and that's not even counting the small ones that are embedded in the rings. We also have a lot of dust that you can even see on naked eye if you're in a very cold, very dark spot at night, that it's the zodiacal dust. But there is also dust in the asteroid belt. There is also dust in the Kuiper belt. So it is everywhere, actually. And that dust, it's generated as a result of collisions and just the evolution of minor bodies and protoplanets in the planetary systems. And so there is also gas as a result of those collisions and those interactions. This is not where we start. This is where we end, right? This is an evolved planetary system. And just a quick overview of what it actually looks, the evolution process. We start out with a very massive disk around whatever star it's forming. And this is, as we have already the star formed, mostly we have a lot of accretion on the star from mostly the gas. And we also have a lot of photoevaporation and dispersal of the gas to the outskirts of the region. So eventually this settles. Most of the dust is located in the midplane of the disk, or settles onto the midplane of the disk, while the gas is still evolving, either towards the star or outside of the system. And as the system slowly evolves, we start to carve gaps. Not see my mouse. You cannot see my mouse, but on the C panel, you see how a disk is carved. The disk is carved, and the gas dissipates, but the dust remains, the dust red particles that you can see there. And it agglomerates into larger dust particles, and we get to the D panel in the bottom right, which is what we call debris disk, where we classically thought that was just dust in protoplanets. The giant planets are potentially already formed in this phase, and we are still forming rocky planets. There is a lot of collision and interaction going on in that phase, and we are still generating a lot of dust between just collisional interactions between the protoplanets and the small bodies. And we think that those debris disks have configuration similar to the solar system, or most planetary systems do, except then you have these very fun cases of migration and architectures of the planetary systems. But we think this is like general view, where we have the asteroidal zone, that it's equivalent to the asteroid belt in the solar system, the Kuiper belt zone equivalent to the Kuiper belt in the solar system, and then we have this dust in the inner regions that it's equivalent to the zodiacal dust that we can see at night, that it's really close to the star. So if you notice this plot or this image, it also shows temperatures, not only distances, and it also shows wavelengths. That is a rough equivalency of how we can detect different types of dust at different distances, and how that dust is heated differently depending on the distance of the stars, just because of the radiation, right? So if we go to short wavelengths, we usually see dust that it's closer to the star, and if we go to longer wavelengths, we see dust that it's further out. And this is always talking about thermal emission, right? But these systems are not just this. We know now, we have plenty of evidence that there is a lot of gas in these systems. And we had this evidence for years, but it was mostly established 5-10 years ago, when we started detecting a lot of gas with ALMA in the millimetric range and the submillimetric range in the outskirts of the systems. So this gas is really cold because it's quite far from the star, and it's very stable. It's mostly emitting, not so much absorbing. Yeah, it's pretty stable, and we find it in a variety of systems with a variety of orientations, but it's mostly CO. In most of the systems, we just find CO. It's usually sort of evenly distributed as we can see it, or as the resolution allows us to see, except few cases. There is always an exception to the rule. And I'm bringing up beta peak also because I'm studying this system with James Webb right now, so I'm very interested in all the characteristics and the morphology of the system. You can see in the top panel the continuum, so that is showing you the dust. This is millimetric regime, so if you remember long wavelengths, that's actually called dust, that it's in theory further away from the star. And this is also tracing larger pieces of bodies, so it's not very small dust, it's actually slightly larger population. Mind you, I'm saying it's larger population, but we're still talking millimeter-sized dust here. And in the bottom panel, you can see the gas, and just right off the bat, you can see that that's not symmetrical, that's not a symmetrical disk. There is a huge clump of material in one side of the disk. This is a result that has been known for years, almost 10 years. You see this paper is from 2014. So we know that gas is present and that it has some asymmetries, and it is basically observed at cold wavelengths, this DCO. But we also see gas that is not as cold. It's in fact really hot. And we have been detecting this gas for many, many years, and mostly in the optical wavelengths, so the calcium 2 K and H lines. So this gas presents, you can see here, I don't have my mouse, but you can see here broad absorption. That's from the atmosphere of the star. That's a photospheric line. It's very rotationally broadened because this is for an A-type star. And on top of that, there is a very small absorption that it's not from the photosphere. It's not rotationally broadened, so it doesn't come from the star. It actually comes from the circumstellar medium. Someone could argue, like, that could be also interstellar. Yeah, but that's not the case for this star. We do think it's circumstellar. And that gas, contrary to the CO that I was just showing, it's actually really close to the star. It's in the inner regions, few stellar radii distance from the surface of the star, and it's also really, really hot just because it's very close. So we're talking thousands of kelvins here. Calcium was the first detection, but I cannot come to Goddard and not mention two really cool papers, one by Aki Roberge 20 years ago, where they detect carbon-1, that it's also circumstellar, so that's not coming from the surface of the star, it's coming from the circumstellar disk. It's gas that it's been heated up really, really close to the star. And if you squint your eyes, you can see that the absorptions vary from one observation to the other, and that's because we have some gas that it's moving around the star, and I'll get to that in a second. And it's not only calcium and carbon, you can also see other materials like Si, in this case, very highly ionized. A paper by Carol Grady, who's also here at Goddard. And you can see it also varies. The two different lines are two different dates, blue line and black line. So we have variation here, so that gas is also moving. So just a summary of this large introduction is most of the gas is cleared at the protoplanetary phase, but we do see gas anyway after the protoplanetary phase, in the debris disk phase. So these gas has to come from a secondary origin. And the most plausible explanations that we have been working on for years is either it's a stellar process, like the star is releasing gas for some reason, winds or whatever, which is very unlikely for A-type stars. Or we could have some evaporation process of material that is really close to the star and evaporating, and you see where I'm going here, I think. Or you could have collisions that it's also releasing that gas. So if we follow the evaporation arrow, which is where I focused my PhD, we can start to talk about falling evaporating bodies, or exocomets. And I would also like to bring your attention to the date of this paper, which is 1987, so a long time ago. We saw, or Ferlet et al., the French team saw, that on top of the very broad photospheric absorption from the surface of Beta Pictoris, from the star, we have some narrow absorption, that it's the circumstellar gas, that it's very stable, but for different line styles, you see there are different dates, and that means there are different absorptions happening in the circumstellar environment of the star. You can see them here, and those are what they call the falling evaporating bodies, because who would call something an exocomet in 1997 when we didn't even have any exoplanets detected, right? But we call them now exocomets. So this is basically what is going on. This is a plot that I always put up because I think it explains the phenomenon very well. You basically have on the top panel, you can see the star that it's spinning, and in the middle of the plot, it shows a comet that it's evaporating, and you can see the tail, and the orbit is also plotted. So as the comet moves from the star and it's close enough to start evaporating the material, you generate the absorptions that you see in the bottom part. One is the narrow one, that it's the stable absorption from the circumstellar gas, that it's stable around the star, and the other one that it's variable and would show in the calcium K and H lines. Just the comment, it's really hard actually to see it in the H line because it's blended with a Balmer line. So we mostly detect them in the K line. And just wanted to play this GIF so you can see how many exocomets we actually find in Beta Peak. I don't think I included it here, but there is a study by Fabian Kiefer from 2014 where they claim that they can detect 2 different families of exocomets just based on the different radial velocities and depths of the comets. So we do see a lot of comets. I think in that single paper, it's like 2,000 different comets. So the point now is that we have around 20 or 30 systems with reported exocomet-like activity. You can check my paper. This is basically the summary of my thesis from 2020, but there is also a very nice paper from Polstrom from the same year where they do a connection, or we do a connection between exocomets and solar system comets. So what's the similarities and what's the difference? If you take a look to this diagram, you can see that most of the variable absorptions and most of the circumstellar origin gas that we detect is actually around A-type stars, so larger stars. Even though we had a pretty uniform sample, most of the results were around A-type stars. Yeah, and the size of the circle is the rotational velocity of the star, but that's also linked to the spectral types. That's a analysis. And I just want to say that this should interest you also because they were exocomets were thought to be an evidence of the planet Beta Peak B in the system. The planet was theorized as a perturbation that was causing the material in the disk to be stirred and thrown inwards. And so that's the exocomets that we're finding. Now that we have another planet, Beta Peak C, we're not so sure how the dynamics of the system work out. So we're still waiting for someone to do all the math and see if we still can have exocomets with B and C both interacting with the disk. And just I thought I also mentioned that in Beta Peak, they also have exocomets in photometry, a bunch of exocomets in photometry. This is the first detection by Sebastian Siva in 2019 when he was just a master student. Like, this is a really cool paper. And you see that these photometric absorptions observed with TESS are not symmetrical, and that's just because comets are not symmetrical. They have a solid nucleus, and then they evaporate the tail. That it's that exponential decay that you see on the right-hand side of the plot in the larger absorption. And these were the three exocomets reported in 2019, but in 2022, Alain Le Cavalier de Setangs published another 30, and with some modeling, they were able to estimate the sizes of those comets. And they could actually claim that the ranges of sizes that they are seeing are pretty similar to the ranges of sizes we see in the solar system for minor bodies, for asteroids and comets, which is cool, but not surprising really, because if the formation mechanism is similar, then you would expect a similar distribution, right? But it's good to have evidence. So we're seeing the comets in spectroscopy and in photometry. Are they the same thing? Maybe, maybe not. The ranges where we see the exocomets in spectroscopy are very small. These objects are really, really, really close to the star, less than a few stellar radii. I put 20 there as an upper limit, but we actually think it's within 10. But the exocomets we see in photometry actually have a wide range of distances to the star. So we might just be seeing two different populations. There is also a range of distances within the spectroscopic exocomets because we are evaporating different elements, right? So we can measure the radial velocities and we can estimate temperatures for the different elements that we're seeing. So my point with this slide is that Fabian Kiefer, if you remember, I just mentioned, suggested that there are two families of exocomets around Beta Peak, and this could be also an evidence of that. Like we could have different families of exocomets with spectroscopic and photometric comets. So I told you about the inner gas, and I told you about the outer gas. Are they connected? Is there any evidence that exocomets play a role between connecting the outer gas with the inner gas? Are they produced in the same events, in the same evaporations, in the same collisions? We did, and this was also part of my PhD, an experiment where we took all the systems that had gas reported either with ALMA or with Herschel. ALMA detected CO, as I showed at the beginning, and Herschel had some carbon detections. And at the moment we did this was 2018. There were these ones. We analyzed 1, 2, 3, 4, 5, 6, 7, 12 of them, plus Beta Peak and Fomalhaut, 15 of them, and Beta Peak and Fomalhaut were not in the paper, but they also follow the same trend. So you can see that there is like a bigger plot and a smaller plot with 10 objects in one, 2, 3, yeah, and 6 and 5 in the other one. So the big 10 ones, those are the stars were having cold gas detections. We also see a detection that could be related to circumstellar gas. So we think these systems have both hot gas and cold gas at the same time. And in the smaller ones, we do have the detection of cold gas, but we do not have any detection of hot gas in the bottom left. And I think it hints you where I'm going, the fact that I also put some numbers there that are the inclinations of the systems. So if you give it another look, the systems with high inclinations are mostly in the range of stars where we think the absorption is circumstellar. The ones rounded in red are the ones that we are like sure that this is circumstellar. We have a dubious one, so maybe, and most of them have high inclinations with one exception. And Beta Peak also follows this trend. So we ended up having like 8 out of 9 debris systems that are edge-on with an absorption that could be circumstellar. And on the other hand, we have 7 out of 8 that are face-on that do not show any absorption. So basically what this means is that we just have a geometrical effect. We have some systems where just because they're edge-on, we can see the gas in absorption that it's transiting in front of the star. But if the disk is face-on, we just don't see the gas transiting. So therefore, it doesn't mean that it's not there. It just means that we cannot see it. So yeah, we thought this was a good result. And we thought, okay, we might have some hints on where to look for gas now. Because if we're seeing the gas in the optical for whatever set of debris disks that we have, maybe we can also go to those systems and search for the gas in submillimetric range, so for the cold gas, which is a much cheaper way to do than the other way around because we need less time on high-resolution spectrographs than we need in ALMA to actually detect this gas. So we went and did the opposite experiment where we took a sample of stars that is in that table, where we had detections of hot gas, so circumstellar gas in the optical, and we just went and looked in ALMA for the cold gas. And you can see there is you cannot see it here because it's, I don't know how to take that out. You only see half of the plot. Sorry, the people in the room only see half of the plot. I just don't know where my mouse is. Oh, I just don't see my mouse. Okay, I'm sorry, Chris. I'll show you later. Yeah, so there is a range of ages, but there is also a range of infrared luminosities, and that's going to be relevant later. So the results of these observations with ALMA, this is data that came down in 2019, so not great for me writing my thesis or the pandemic, but it eventually got done. This is what we see in the continuum images, and you can see some detections. There is one there, please, I promise. We have a weird object that has like 3 point sources, and we still don't know what that is, so if someone wants to go look at it, we think it might just be background sources. We do have another source on the right, that on the top panel on the right, that we think it's just a background source as well, because it's not coincident with the position of the star. The astrometry just doesn't work out. And then we have 2 detections in the continuum, one for HC110411 and another one for HC158352. And we think those are actually related to the star. We think that's dust bound to the system. But there is one object missing from this plot because I gave it a separate slide, and it's HC36546. And this has quickly become one of my favorite objects because I think it's super interesting. I'll get to that in a minute. So for this object, we do have detection in the gas and in the continuum. So the continuum is the right panel. We do see the disk. Our beam with ALMA was pretty big, so our spatial resolution is not great, but we were not aiming for characterizing the morphology of the system. We're just aiming for a detection. And we do get one both in 12CO and an isotope of 12CO, that's 13CO, in the same transition. And that allows us to calculate the temperature of the gas and also estimate the masses. So we end up with a disk that it's heavily inclined, or that's what we can extrapolate from the data that we have, around 80 degrees, and that it's fairly big, semi-major axis of around 200 astronomical units. So this disk, it's actually pretty interesting because, I can give you just like the SED. We can estimate also the gas, the dust mass, just from the millimetric point. That's the point to the bottom right, in red. That's the continuum photometry, and with that value, we can estimate the larger population of grains in the system. So we assume that that's going to contribute more to the total mass of dust. So we basically, using just the ALMA data and some temperature calculation from the rest of the photometric points, we can estimate how much dust we have in the system. And we can also try to do that for the other systems, particularly for the ones where we actually have detections and not just upper limits. So that's for the dust detection, but for the gas detection, we actually have some very interesting results. And the first one is the top left panel, which shows the 12CO line with velocity. And you can see that it's very clearly asymmetric. So the gas in this disk is just not symmetric, and we don't know why. And if you recall, I showed the beta peak image where you could also see that there was a clump in one of the sides. So this might be also a similar thing, maybe not as exaggerated as a big clump like in beta peak, but it could be something similar, right? We could have some big asymmetry in the gas component. And you can also kind of hint it in the 13CO on the top right, but we just don't have the resolution, the spectral resolution to actually claim that there is an asymmetry. And we could also very nicely measure the rotation of the disk in the bottom panels, both in 12 and 13CO. Yeah, we're getting a lot of information from the gas, but we just need to get more or better spatial resolution. So I told you the system was very interesting, and this is the background of this system. I just told you that it has a detection in the continuum in ALMA. It has 12 and 13CO detections in ALMA, possibly an asymmetry in the gas, but it also has history where Casey Lees in 2017 found that there is actually an overabundance of carbon. And you can see it in the bus spectrum in yellow there, that it just has a very conspicuous emission like around 9 microns, and they attribute that to carbon being in the system, to a large amount of carbon being in the system, which could potentially indicate that there was a large collision recently. And we also have detection of exocomets or exocomet-like variability in the spectra, in the optical spectra, as I showed before, those narrow absorptions that appear at different radial velocities than the star that are just really variable, and we can see it in like 3 different days how the event develops at around 20-something, 25 meters per second. And we also know that it is a very bright disk in scatter light. Unfortunately, it's quite far, so we do not get a great spatial resolution from ground-based. It's going to be really hard to look at the morphology of the disk, but we know its edge on. The sizes they see in the inclination and the sizes they see in the paper by Thane Curry in 2017 are very similar to what we find in ALMA. So we think most of the dust it's located in a similar plane, a similar disk of similar size. So there's a lot going on in the system. We just have to find the planets that we have to go look for them. So maybe with James Webb, who knows? Yeah, and so this is a general result also from that paper where we try to find gas in a bunch of debris disks where we have only that detection of HD 36546, which is number 4 on the top left of the left panel. You can see it at around 10 to the minus, close to 10 to the minus 1 Earth masses of CO. So it actually has a lot of gas compared to other debris disks, but it's also very young. The estimated age of this system is between 3 and 10 million years old. So very, very young. Just some people have called it a transition disk in the literature, actually. But what happens with the other disks where we didn't get any detections? Well, if you notice, most of them also have very low dust masses. And there is this very nice paper by Quentin Kroll from 2017 where he claims that there is a correlation between the infrared luminosity, so the amount of dust in a system, and the CO mass, because you're generating them the same way. The CO and the dust are being generated by collisions or evaporation or whatever. It's the same processes. So if they're the same processes, if you don't have a lot of dust, you're also not expected to have a lot of gas. So this might be just what we are finding. If our debris disk is very faint, it means we don't have a lot of dust, and therefore we won't have either a lot of gas. So we're pretty limited to just being able to study the gas in really bright debris disks. So I'm coming back to my previous question, which I tried to solve with this to study from the spectroscopy to the submillimetric regime. Is the inner gas in debris disk somehow connected to the outer gas? And do exocomets play a role? And if so, is that transport mechanism observable? Can we have any evidence of how that gas or how those exocomets move inwards from the outer regions? There was one attempt, I would say successful attempt, from the ground by this group by Trotman et al. In 2011, where they tried to aim for the CO fundamental row vibrational modes. So that's a different transition from what we observed with ALMA, and it's supposed to be in an intermediate region. So the gas we would see with ALMA would show up at longer distances from the star, but this CO fundamental could be slightly closer in, just because you need less energy to excite it. And what they found was some very, very narrow and small lines in the beta spectra that indicate that there is some warm, not so cold, but warm CO in beta pictoris. So that could indicate that there is gas being produced also in the intermediate regions. So that would tell a very nice story of how they all connect. But this is from ground. You see those lines are really small. If you look at the top line, you see the very small absorptions that are marked with the transition names from 1 to 0, R3, R2, R1, or R0. And the bottom line, the bottom spectra, it's actually their observations where they show all the telluric lines that they had to then eliminate from the spectra. The line in red is actually the telluric model. So most of what they're getting, most of the signal that they're getting, it just comes from the telluric lines at this wavelength range, where the sky, it's brutal, it's really, really bright. So yeah, so how do we do that for other stars? Beta Pig is a really bright star. It's really close in. It's only like 20 parsecs. So it was the perfect subject study for the experiment. But if we want to do it with other stars, we cannot do it from the ground. Cue James Webb, right? In order to try to replicate this experiment, we applied for time. We got the time in cycle 1. These observations are halfway done. We had a couple of observations failed, so they're going to be repeated hopefully soon. By the end of the summer, we should have all the data. Yeah, so the idea was to go for those low vibrational excitations of CO. So we just went for NIRSPEC, that it's in the near infrared. I feel like I'm preaching to the choir here, talking about James Webb at Goddard, but with me. And so we're going to the 3 to 5 micron grid filter. So it's not actually 3 microns; it's more like 2.8. So we were also trying to get that tail of the water band, that it's at 2.7, 2.8, 2.9 micron. So far, I can tell you, so far we don't see any water. Or you would have heard from me before of this. The only caveat here is that we're getting very low spectral resolution, and someone can say, like, well, 2700 is not that low. But the spectra that I just showed you from Trotman et al. Was, I think, like 40 or 50,000, so much, much higher spectral resolution. So that's going to be basically our problem when trying to find the CO lines. Yep. So, and well, we went for the fixed slit, for the largest one to avoid. Yeah, I think we went for the largest one. In the end, after a lot of deliberation, to make sure we got all the light in there. So I can show you some of the results. Target 1, I put target 1, but there's no secret. I already presented this at a couple of conferences. This is HD36546. So that object, so that system that I was telling you about. And we do not see any CO. CO should be between the 4 and 5 range, around 4.5, and there's just nothing there. Those are just stellar lines from the spectra. There's potentially nothing interesting in the spectra except for that near-infrared excess that starts around 3.3 or something. I was very worried that this was actually an instrumental effect, because there have been a number of problems with the data reduction from NIRSPEC, but apparently it's not. We're pretty confident this is real. It deviates from the model. The model was fitted to the optical data. We also have very high spectral resolution optical data for this target. That's where we found the exocomets. So we are very confident, or pretty confident, on the parameters we're using for the model. And it seems to fit well at shorter wavelengths, just not at the longest ones. So yeah, that's pretty interesting, because that near-infrared excess, if you recall from the beginning of my talk, it's pointing us towards really hot dust, that it's very close to the star. That would also fit in this scenario where we have exocomets that are evaporating close to the star. And we're seeing the gaseous features, but apparently this could also be proof of the dust features. And then we have target 2, that it's HD 1488, where we do not have CO absorption, but we weirdly have CO emission. and we were not expecting it. We were expecting the CO to be in absorption because these systems are supposed to be edge-on. The CO is transiting in front of the star, and it's producing absorptions. So yeah, we're working on the interpretation of this. I have to say that the slit is fairly big, and these targets are not close. So we could just be getting a lot of the disk within the slit, and we could be getting emission from it. But I have to say it's like a significant emission. So Cicero Lu, who is a student at JHU, she's about to graduate and move to the Gemini team in Hawaii. It's working on this paper, so as soon as she submits her dissertation, hopefully in a month, she'll start working on it. So stay tuned for this paper. It's interesting. And that's basically my talk. I wanted to summarize a little bit this. I hope that you got clear that the presence of gas in debris disk can be hinted and detected at different wavelengths. So it's important to keep an eye out from all the different absorptions and emissions that we can see, so we can fully understand this gas. There's an importance in the analysis of this multi-wavelength studies because, for example, it has kind of confirmed that there is a sort of correlation between the inner and the outer gas. They're both present in the systems. We just can't detect them if the orientation is not right or is not edge-on. Then I want to highlight some of the results from AC36546. It's a very cool system. We have detected 12 and 13 CO, so it has cold gas. It also has hot gas from the spectroscopy, from base spectroscopy. It has, I think I didn't mention it explicitly during the talk, but it has several debris belts similar to what I was showing at the beginning of the talk, the asteroid belt analog and the Kuiper belt analog. So there is a distribution of the dust in the system. It is very carbon rich, so it might have had a recent collision. And it has exocomets. We have detected variability in the spectra that we think is related to evaporating bodies. Then, as an overall result from that study, we can also say that the brightness, or the infrared luminosity, or the mass of dust that we have in a debris disk might be connected to the CO mass, and therefore we are not going to be able to measure the CO if the debris disk is very faint, just because, again, we're not producing enough CO to be detected. And I hope I also convinced you that James Webb, it's a good tool, even though the spectral resolution is not great, to try to study these intermediate regions of these systems and potentially study a transport mechanism. And just the ongoing work I have with this regard, it's the finalization of the observations for the program GEO 2053. And we're also working in the analysis with 2 papers on the way that hopefully this summer will get boosted after Cicero finishes her thesis, and I have some time to work on that. And as of yesterday, there is a very exciting new accepted James Webb Cycle 2 proposal by Luca Matra, where they will follow a similar study as my proposal, as the GEO 2053, but they're going to look at shorter wavelengths. So they're basically aiming for the water. Well, I was aiming for the CO. So fingers crossed, everyone. Hope we finally find some water in a debris disk. And that's my talk. Thank you so much, everyone, for coming.
Yeah, you can keep that one. Thank you so much for the talk. That was really, really interesting work, Isabel. So we have time for questions. If anyone has any questions online, feel free to raise your hand, or you can just post them in chat. But did you want to go first? Yeah.
So I'm totally blown away that we've apparently detected thousands of comets in Beta Pic. Incredible. So what can we say about these 2 families that we think we know about now? What aspects of their orbits can we constrain? Do we know the orbital periods or relative inclinations or anything about them?
Yeah, so I think Flavian Kiefer reported 2 different sets of inclinations and orbital distances. So there are comets that are further away and comets that are families of comets that are further away and families of comets that are closer in. But yeah, there is not that much we can say because we're basically making an extrapolation of the combined measurements that we do. It's really hard for a single comet to estimate their orbit. There is an attempt that Grant Kennedy made. I think the paper is from 2019 or 2020. But you need to follow up the same event to actually measure or try to measure an acceleration and then establish an orbit. That is really hard to do. So for that paper where they claim the two families, they're just basically making assumptions based on the radial velocities and the depths. So they also think they have distribution of sizes in the different families. They have two different distribution of sizes in the two different families. Yeah, I think in that paper alone, they reported like 2,000.
Yeah, I have another one. You were showing photometric detections of comets. Do we see these in the Kepler data?
Yeah, good question. So that very famous Tabby star has these single transits that many people are claiming are exocomets. And then there is a couple of, I think, F-type stars, which is really interesting, actually, because we don't see any exocomets around F-type stars in spectroscopy. But there are two, at least, that were reported by Rappaport in 2018, I think is the paper, that are around F-type stars. So the question is, like, can we see the photometric signal around F-type stars, but not the spectroscopic signal? Like, what's going on? And that could also be related to the fact that the distances potentially, let me go back to that one. The distances are potentially different. So you might have just the spectroscopic comets closer in, and for whatever reason, the comets are already like blown out or burst or whatever for the different spectral types. So the A types are just a sweet spot for those comets.
So I guess I'm confused though, because if we found 2,000 comets around Beta Pic,
yeah,
sounds like you're saying we found a handful, all of the Kepler data. But why such a huge discrepancy? Is it that Kepler, that we need better precision than what Kepler provided?
So this paper actually is, you don't see it, but it's from 2023. It's accepted as of yesterday. We did try to find exocomets with Cheops. And one of the reasons we think is that we don't find them is that it's just so sporadic. You need to have a very long long-run observation of these objects. And this was done for a handful of exocomet host stars because they're A-type stars. So people are not looking for planets in transits around these stars. So we just don't have the data, and these are sporadic things. So what we did was look at one object for 48 hours. We don't have any comets, but it could just be that there are no comets in those 48 hours. So we really don't have enough data to make an assumption of what's going on. What we do know is that Beta Pic is not the norm, is the exception. Because we also don't find any other star with that level of comets in a spectroscopy.
All right, are there any questions online? I think there's one. You can go ahead.
Hi, I'm Panayotis Zanavaris. So I don't actually work in the field, so I'm just trying to understand though, because I think it's very interesting. Can you say a bit more about how you were actually looking for the reverberational lines around 4 microns with JWST, like the other people had found them with the ground-based data, then you didn't find them, but somehow the near-infrared excess is consistent with that. So how does all this get together? You don't find them, you see the excess. So what is actually, happening? Is it the same model? Do you need to change the model?
Yeah, so I apologize because I might have been confusing in that part. The near-infrared excess is not directly related to the presence of CO at the same wavelength, right? So we're seeing two different things. This near-infrared excess is dust that is being thermally heated up by the star.
Right.
So it's dust that it's really close to the star. Oh, sorry, it's dust that is really close to the star, okay? But the CO would not be located as close to the star, the CO in a low vibrational mode. So you need a certain temperature or energy to excite the raw vibrational mode of the CO,
Right.
and that just corresponds to a thermal location that it's further out from the star. So the dust that we are seeing with this infrared excess is not located at the same place as the gas that would produce those absorptions. So we can have the dust very close to the star and not have the gas in the intermediate regions. It could also be that we are having that gas in those intermediate regions, but because we are very limited by the spectral resolution, we are not seeing it. So if I go back to this plot, you see that those lines in the top spectra are really, really, really small. It's just a very small fractional value of the continuum.
So even though you use even though you use JWST, it's another object, so it's more challenging.
Yeah, so we have only used James Webb to look for these gas in a handful of these objects. So like 3 objects of these 5 have been observed so far, but this one is from the ground. The thing is, from the ground, you cannot do this, and we tried. There is also a paper coming out soon around a different star that also has CO gas detected with ALMA. We tried to look for these very small raw vibrational absorptions, and we didn't find anything just because the sky is so noisy. Beta Peak is really bright, and this was done in Beta Peak. But the moment you go to a fainter star, even if it's slightly fainter, you're going to be totally overcome by the background, and it's going to be basically impossible to detect these very small lines. And with James Webb, we have the opposite problem, right? Like we have the sensitivity. We don't have the background. We don't have any background bothering us. But the spectral resolution is so low that we're just going to diffuse those lines, and they're going to be even less shallow than that. So it's going to be even harder to detect them. We need really, really high signal-to-noise ratios. And that is also something that is happening right now. We're trying to improve our data reduction and our extraction of the spectra so we can go to higher signal-to-noises and potentially detect smaller amounts of gas.
Thank you. Very
I don't know
nice.
if that answered your question.
Yeah, thank you.
All right. Any other questions online or in the room? Kind of one, just building off of Chris's first question, that blew me away too, the number of comets in that system. What is the next system that we either know about or maybe you are thinking about is going to be another one that we get a lot of detections for?
Yeah, that's a terrible question. I don't think we're close to finding a place as prolific for exocomets as Beta Peak, at least not the way we're looking for them.
Okay.
We're looking for exocomets either really close to the star with a spectroscopy, or with looking for exocomets in photometry, where it's actually really hard to find them because they're very sporadic and they're not that many. So I hope that with the event of like the test data and then Plato, it's also going to fly hopefully soon. We're going to have much more detections in photometry, but as for the stars that we have looked for exocomets in a spectroscopy, no one's even close to what we see in Beta Peak.
Gotcha.
And none is going to be close at any point in time.
Nice.
Because we have done, like, again, the first detection was in 1987. We have done a lot of follow-up of a lot of systems. I just spent 40 or 50 nights in high-resolution spectrographs trying to follow up these systems, and we didn't find anything close to what we found. And, well, that's actually not true. We found 2 stars where we had a lot of variable signals. None of those were exocomets. So it's also easy to confuse them with other phenomena like pulsations of the star, which are not common in A-type stars, but it can happen if they're delta Scuti or whatever. So it is really tricky.
Thank you.
Yeah.
All right, any last questions for our speaker? All right, well, let's thank Isabel again. Great talk.
Yeah, thank you, everyone. Thank you for joining online.
Yeah, thanks everyone online.
Thank you for having me.
All right, I'm gonna end the meeting here.